Okay. Then S on T would be equal to ABA hashtag Abatsaba. And then we calculate the prefix function of this. This would be 0, 0, 1, 0, 1, 2, 3, 0, 1, 2, 3. Okay. So what would be the answer? How to find the occurrences of the word ABA in that string, assuming that we know prefix function. The answer.
Если встречается.
Если.
Если встречается, например, число с размером m, то occurrence.
So the answer will be if P of I is equal to m, right? So the length of the word, then occurrence in what positions occurrence happens then? So I would be the last symbol, right? And
I minus m.
I minus m. Just I minus m. So
Minus
this
1.
is minus plus 1.
Plus 1, yeah.
Okay. So that will be occurrence. So this is the first position. This is the last position. Who was that speaking?
Me.
Arjan. Oh, perfect. Good job. Okay. So that's it. You will find just the. So if I find the m at position I, so if I position I in the right string, I'll find pi equals m. So that would mean that from here I found the prefix of length m, like the suffix of that string of length m that is equal to the prefix of that string. The prefix of that string is just the word w, right? So that means that the word w is appearing here as well. But that's it. Very simple. Very simple. Okay. So this step. So third step takes of n plus m time, the length of the string t. If you will be able to calculate prefix function in linear time on n plus m, then that would be solution with n plus m time, and that is what we are going to do. Any questions? Okay, no questions. Then let us proceed further. Let me just draw a line so I'll be sure when should I be staying. Непонятно, конечно, ровно или нет, но ладно. Okay. Okay. So we now come to the implementation of the KMP algorithm. KMP algorithm implementation. First step. Oh, not first step. First try. So we can do that in n times m, right? So we now have string s of length m. We need to calculate the prefix function. Oh wait, sorry, n square. We just have a string, only one string, and we need to calculate prefix function. Okay, so what are the options? So if we want to do that in the linear time, in this n square time, what we can do? We can just iterate over the string. So let us assume that we are at the position I. So what we can do, we can just iterate actually, I don't know how to do that in n square time.
It's n cube.
Yeah, we can do that in n cube time then. I don't know how to do it in square time, but I know. But the easiest one is the n cube, right? So we fix position I. So for that position, I want to calculate the prefix function. So I'm just iterating. I'm just iterating over the length, over the answer length. And then I'm just comparing this string to this string. Okay. So I iterate over the answer and then compare the strings from j minus I plus 1 to I with from 0 to j minus 1. So for I from 0 to n, no, from 1 to n, 0 is always 0. Like p of 0 is always 0. For j, from what? From the largest length is going to be I minus 1. J equals I minus 1 to 1. And just try to compare string from 0 to I. Sorry, not I. From 0 to j. If it's equals to string from I minus j plus 1 to I. So both of them are of length j. So if so, I set p of I equals j and break. So I calculate.
Yeah, it's j when I means j plus 1 j.
No, it's I.
Second string.
No, it's I. Because yeah, I want the string to be the suffix of the prefix I. So it must end at I. So I just take the last position as I and then take last j letters of that string, of that prefix of I. So this is going to be I minus j plus 1. This is going to be I actually. Because the prefix, if we index from 0, this is going to be I. Okay, that's it. That's the entire algorithm, which works in n cube time, because this is big O of n, this is big O of n, this is big O of n. But that is not effective. We don't want to do that. What we're gonna do, smarter than that. Second try. Linear time. So the algorithm is quite tricky, but it is beautiful in some sense. So what we're gonna do, we're gonna start with the string s. So this is our string s. This is our string s. This position 0, this position n minus 1, and let us assume again that we are at position I. Okay. So once again, we're gonna do that for I from 0 to 1. Like we're gonna obtain the answers one by one, starting from position 0, then position 1, then position 2, and so on. So we calculate prefix function value by value. Value by value. So I calculate P0, then P1, then P2, and so on. Okay, so assume I've calculated. So P0 to the ta, P of I minus 1. Let us calculate. Oh, so it's going to be we. Let us calculate P of I. Okay. So what it says, we're gonna do that. How we're gonna do that? We're gonna just take the. So let us consider position I minus 1 and its prefix. So what's the problem with first try is that we just compared everything we can compare, right? Which is not good enough. We do many encoded, like we do many comparisons of the strings that are unnecessary. For example, which fails at the first letter, which fails at the second letter, so on. So now we do smarter. We're gonna do just comparings that will increase our answer. Okay, so I'm sorry. We're gonna do comparings that are actually like make sense. So let us assume P of I minus 1 matches. So on the previous step, we found such kind of strings. So we found this. So this is I minus 1, I minus P of I minus 1. So this is this position, this is this position, and so on. So this is P of I minus 1. Let us assume we found on the previous step that this string is equals to this string. Okay. So what can happen on the I string is that we just need to compare then if that symbol is equals to this symbol. Symbol at pi minus 1 plus 1 is equals to symbol of I. If that happens, then this is going to be the largest answer. So let me just write it down. So, okay, this is the setup. So if S of I is equals to S of it's pi plus 1, pi minus 1, S of pi minus 1 plus 1, then P of I is equals to P of I minus 1 plus 1. Okay. So why? Because if so, we can do that. So this is for sure would be the largest string, right? This is for sure would be the prefix that is the suffix of the prefix I, which is prefix of S, right? So that we know for sure that this equals to this, in other words. Okay, but why it is largest prefix? This is largest prefix because it was largest prefix for the previous symbol. So this string is the largest prefix that is on the suffix of at the position I minus 1. If that's so, then if we add the symbol X, that would be again the largest prefix, for this position now. Why it is so? It is so because assume we have a string s, and so assume just the largest prefix that could exist in the world, right? The largest prefix that could exist of this, like the largest prefix of that, like the answer for the ith position. Just let me say like that. So in order not to confuse you. So this equals, okay, let me just write it smaller. This is equals, no, a bit larger. Okay, this is equals to this. Okay. So let us assume these green rectangles indicate the largest answer for position I. So the value of the prefix function. The length of that green rectangle is the value of the prefix function I, like actual value, not that we want, not what we found, but the actual value. Then let us step back at position I minus 1 at the previous position. So then for this position, the answer would be this rectangle again, just shortened by one position. The answer to position I would be shortened by one position of the answer for position I. The answer for position I minus 1 is almost the same as answer for position I. Okay? Okay. Any questions, guys? Does it make sense? So this is the example of what we have here. For example, you see for position 4, we have the answer AB equals AB, right? So we have this string as an answer. So the length of that string is an answer 2. And then for position 5, then we have the answer 1 larger than the previous answer. Or vice versa. If we consider the value of the prefix function at position 5, it is equals to 3, then for the position 4, it would be at least 2. So that would be 2 in this case, or maybe it would be larger, but it is at least 2. Okay, this is the case if this happens, if this position is equal. So if these two positions are equal. But what if it is not? What if it is not? Then what we can do else, so what we can do, so what's the next prefix that could be here? We can use the fact that this string now, so this green string is equals to this green string. Okay, so we want to find the next candidate for the continuation by this symbol I. So the first candidate was this string, right? Next candidate would be something like this, right? Next candidates, which for the continuation would be like this. This is pretty much the same as we did in the first try, but on the first try, we just compared everything, right? Like this, one symbol by symbol. We remove just the first letter and then compare it to the corresponding prefix. But instead of doing that, we can say, okay, what is the next candidate? We can ask, what is the next candidate for the equality? And actually, we can obtain it very effectively with just our smart head, with just our smart brain. So what we can do, we can say, okay, so the next candidate will look something like this, but that is actually the suffix of that string, right? Then we can find the copy of that here. And as soon as we found the copy of that here, we can just ask, okay, what is your largest prefix? What is your largest prefix that is equal, largest suffix that is equals to the prefix? So we want to find somebody. So let us assume that the answer will be here. So this is going to be our next candidate. Okay, once again, so we've checked this. Oh, wait, I want to write it in that color. So we've checked this. This candidate, the previous positions candidate. Okay, it didn't work well. Assume that this was the symbol y, not x. This symbol is with this symbol is not equal to this symbol. Not a big deal. We say, okay, who's the next candidate? The next candidate will look like this. We want to indicate, we want to find for sure who is the next candidate. So this candidate is the suffix of that green string on the right, or that green rectangle. This green rectangle is equals to this green rectangle. By rectangle, I mean the string enclosed in this rectangle. Okay, this string is equals to this string. So this candidate will have a copy here, right? And this copy is actually would be like if you take the prefix, the value of the prefix function at this position, at position p of I minus 1, we'll find that it will have its like the copy of that and the prefix. So that is going to be our next candidate. So we just want to say else if s of I is equals to s of p of I minus 1 p of I minus 1. Мне надо было все-таки с единицы начинать, ну ладно. P of I minus 1 plus 1. Because I'm taking this position is, this is P of I minus 1. So this is P of I minus 1. And I want to find the next symbol here then, which should be equal to y. And if it's not happens, then again I'm providing this. I'm doing this procedure. And once again taking this string, I want to find the next candidate for that. It's going to look like this. The next candidate for that, we will understand that, we will know that, okay, this guy has a copy here. This is his copy, and we will find the answer of prefix function here, which is has its own prefix and suffix. So that's the largest prefix would be the value of the prefix function would be the answer at this position, would be the answer to be the next candidate here. So it would be indicating the length of the next candidate here. So we will find the next position of this guy and compare to I, and so on. Then, then P of I equals P of I minus 1 plus 1, and so on. So that's the entire algorithm. So we just do P. We just, instead of just taking the previous value, we just go deeper and deeper. So the next step will be P of I is equals to P of I minus 1 plus 1. Okay, and so on. So let us consider an example, and so on, and then we will get, eventually we will either finish this process because P of I at some point, P of I minus 1 will be at some point 0, then we will say that, okay, this is 0 again. Or we'll say that, or at some point we will assign P of I the correct value. So let us consider the example again. Example. A, B, A, B, A, B, A, B, A, like this. B, A, B, A, B, A, like this. So this is string S, this is string P. This is prefix function. Here would be, in this line will have a prefix function. Okay, so this is 0. This is 1. This is 0. This is 1. Okay, this equals to this. Then for position B, we'll try to extend this answer for position B. So we'll have 2 here because this position is equals to this position. So now we found that this equal, okay, this equals to this. Okay, then we face position A. So at this position 0, 1, 2, 3, 4. This is 2. At position 4, we'll see that, okay, we on the previous step we had this equals to this. Let us try to continue that. So A equals to A, then, okay, this is 3 then. We now know that ABA equals to ABA here. So you see they overlap in this case. Same for B. We'll find that B equals to B, then we have ABA equals to ABAB. ABAB equals to ABAB. So this is 5, ABAB, ABAB. So let me just clear this up so it will be understandable. So this step we have ABAB. Okay, so then блин, мне не нравится этот пример. Давайте другой пример сейчас. Давайте вот так вот. Вот так вот давайте. ABA, ABA, B, AABA. О, вот такой хороший пример. Okay, so this is 1 again. This is again 1 because okay, we see that previous string had answered this like A equals A, and on this we will try to increase it. We'll compare A to B. It is not equal. Then we will say okay, P of we know that P of 0 is equals to -1. We will set that like that, or if we start from 1, then so but by definition we'll set it to -1 actually, just for convenience. This is like technical detail. Then when we ask at position 3, we try to compare these guys. Okay, they're not equal. Then I will take the prefix. So P of I minus 1, right? So that would be, so P of I minus 1 is 1, right? Position 1, we have 0. P of 0 is equals to, oh, it's actually should be 0 now, right? P of I minus 1. So P of I minus 1 is equal to what? So I equals 3 here. P of I minus 1 is equal to 1. So this is 1. P of 1. Oh, вообще давайте лучше с единицы индексировать все дело. Так будет проще на самом деле. Если с единицы индексировать, тогда вообще просто. Ну тогда я это все для индексации единиц писал на самом деле. Okay, so 0, 0, 1, 2. Oh wait, 1, 1. So типа вот так вот P of 4 minus 1. So this would be P of form P of 3. P of 3 is equal to 1. P of 1 is equal to 0. So plus 1. So it means that 0 plus 1 equals 1. So we want to compare position 1 with position 4 then. We compare it, it is 1, it is, it works, then we say that it is equal to this value plus 1. Okay, then we at position B, we'll see that, okay, we know that this equals to this on the previous step. Then we'll try to continue. Okay, it works. 2. Then it works again. 3. Then at this position, ABA, we have ABA equals to ABA, but here it is at position 4, we have A. So this is going to be, oh, sorry, not 0, but this is not going to work. The previous answer will not going to work, as like we're not going to work. The previous answer for the previous position will not going to work for that string. So what we're going to do, we're going to say, okay, where we are, yeah, here. So we're going to say, okay, we then take P of 6 minus 1 is 5. Oh, 7 minus 1 is 6. P of 6. What is position P of 6? P of 6 is 3. So it's here. We take the end of that string, and then we take this position. Oh, I'm sorry. We take this position 3, and then take the answer to the position 3. It is 1, right? So this is going to be P of 6 is equals to 3. So P of 3 is equals to 1. So we want to continue then this prefix. So to say that, okay, maybe this prefix is at the end of the string plus this symbol. We compare this symbol to this symbol and it matches. Then we say that the answer would be 2. Okay, then again, we add the symbol A. We had AB equals to AB. We add the symbol A. It is there. So we write 3. Then for this symbol, ABAA, the next symbol is A again. So we write 4, we write 5, we write 6. Okay, so that would be a prefix function for that string. So let me write it back. AB, AAB. Okay, guys, does it make sense?
Можно вопрос, почему мы во второй, скажем так, строчке не прибавили единицу вот к P от 6?
Вот здесь?
Вот еще ниже, вот префиксы.
Вот здесь? Не, ну да, я просто считал, да. На самом деле, да, ну, то есть надо написать здесь compare positions P of 6 plus 1 and I. То есть вот эта позиция будет равна P3, это было 1, плюс, ну, позицию 2 и позицию 6. Ну, в этом случае было. Позицию 6. Нет, позицию 7, сори. То есть это для I equals 7, по-моему, да? Да. Ну, а для I equals 7, если посмотреть, то, думаю, понятно станет, что вообще алгоритм делает. Давайте еще раз посмотрим. И вообще есть, ребята, вопросы? Всем понятно или вот кого-то все-таки непонятно и стоит повторить еще раз? Не стесняйтесь. Ну, давайте для I равно 7 повторим тогда. Так, ну, вот здесь как бы, по идее, 1, 2, 3 могло быть 4. Но не стало. Почему? Потому что вот мы смотрим на этот символ. На предыдущий раз было АБА. АБА равно АБА. Ну, давайте попробуем продолжить. Ну, четвертый символ, то есть здесь я говорю опять compare, pos, ну, вот так вот, даже не pos, s of 7 and, то есть здесь опять s of 7 and, это s of this, and s of paired 6 плюс 1. 6 плюс 1 было у нас что? 3. Вот она, да? Вот эта позиция P6. И плюс 1 вот этот символ. То есть мы как бы просто пробуем продлить. Вот хорошо, они не равны. Not equal, да? То есть вот not equal здесь. Ну там мы что делаем? Мы говорим, вот эта строка равна вот этой строке. И давайте посмотрим ответ вот здесь вот. Префикс функции, ответ префикс функции вот здесь вот. Потому что мы хотим следующего кандидата на продление, да? А следующий кандидат на продление оказывается вот, ну, так как вот эта строка равна вот этой строке, вот это, ну, тогда вот мы здесь можем взять ответ в этой позиции. Он будет равен 1, да? То есть вот, значит, вот эта строка, вот этот префикс, он как бы здесь лежит, вот здесь вот. Значит, это, ну, это будет следующий кандидат, потом в силу максимальности префикс функции в этой позиции. Вот. Ну и вот это, пытаемся вот этот префикс продлить здесь. Вот, позиции B. Получается. Вот у нас тогда ответ 2 получается. Мы нашли вот эти две строчки. Окей? That's it. We now want to analyze. We now want to analyze what is the complexity of that algorithm. So this is most interesting part of that algorithm, because it is non-trivial, but it is linear time actually. So you see, we do many comparisons. So we actually do, okay, we iterate over the array, also over the string, which is already linear time, right? So then few the comparings will only increase that linear time, like maybe multiply by some number, but maybe by n, because at some point it may look like it is n squared, right? Because for each position, we may do many iterations of that p of, and so on. Turns out that complexity is linear. So let us write pseudocode, and then we'll understand why it is linear. So let us analyze it. So that would be, so let's say, or maybe we will try to write the code in reality. Is that week 11? Is that week 11?
Yes.
Great. File ACP KMP. Okay. I'll remove this. So the KMP will return vector of integers. KMP, it accepts string and returns vector of integers. So we initialize vector p of length n, initially filled with zeros, where n is length of the string. All right. Then what we do? So I explained you. I explained you zero index based implementation. One index based actually. So here we should modify it in the following way. We will say that since so in this picture we will actually change it a bit to say that p of I minus 1 is actually a symbol that we want to compare with. So so we will remove this plus 1 here. We will remove this plus 1 here initially, and so on, because we have a string s. string s from starting from 0. And then we'll add position I. So P of I would be, so position P of I is actually this position. So this is the length P of I. This is the position P of I. This is this string from 0 to P of I minus 1 is this string, and position would be this. So we want to compare this with this. And then we want to compare P of I minus 1 and so on. Okay. So we iterate from 1. So position 0 would be equal to, I guess, minus 1 then. Oh no, to 0. Okay, P of 0 is 0. So we set it 0 initially. So P of 0 is 0. And then we iterate over this. Okay. Sorry, not strictly less than n. So we say that, okay, we create j equals P of I minus 1. Say that, okay, j equals P of I minus 1. We say, okay, while j is larger than 0 and P of j, S of P of j, oh sorry, S of j is now equals to S of I, this is this comparings. S of I equals S of P of I minus 1. So we do j equals P of j. P of j minus 1. So you see here, so we started from, we assigned j equals this, and then if it didn't work, we say that, okay, j is equals to P of j. Oh wait, P of j then. Then we actually should write it like this, and here minus 1 here. У кого там включился микрофон, ребят?
Ой, извини.
Okay, so so this is the position I. This is position I minus 1. So P of I minus 1 is somewhere here. So position P of I minus 1 is here. Just should actually write it like this. And if it didn't work, then we should do P of, this is P of I minus 1 minus 1. So we set that to J actually. So we should, so this is this, so J is the symbol that should be equal to I. And if that didn't work, we pick previous, like we step back on one symbol back, we step back on the one step and take the prefix function of that string. Okay. So, and finally, at the end, what we can do, we either can have the case if j equals 0, or we have the case that this is not, this became equal. If this became equal, if j equals 0, then we leave it as this. Okay. And then if it's s of j is equal to s of I, then we should increase j by 1. Okay. And then we say that P of I equals to j. Return P. This is a short quote of huge explanation. And now I want to just now I just want to output it. Cout P of I. Just like vector P is equals to KMP of that string, and then CZ of P, then p dot size p of I out like this. Okay. Week 12, week 11, G of KMP. Okay, Abatsaba 001 0123. That's correct. And then what's the string? Oh, this string. A B A A B A B A A B and A at the end. So here, what? Let us compare it. 001 1 2 3 2 3 4 5 6. Yeah, that is correct. So yeah, so code-wise, it looks like it is n squared because this is linear time. This is big O of n, and we don't know how many iterations we do here, but looks like many, right? But in reality, what happens is that it is again linear. Why? Because how many jumps we can do here? So the question is how many jumps we will do here. If you take a look at the transitions, of the transitions we made here, so either this or this, so else and so on. Either this at any moment of time. So the P of I is not larger than P of I minus 1 plus 1, right? So this and this as well. So at each step we might remove. So you see, at each step, it increases by 1, right? P increases by 1, like in the best case. In best case, it just increases by 1, by 1, by 1, by 1. Okay? So if we draw the graph of the function P of I, it would look like this. It can increase by 1, increase by 1, increase by 1, increase by 1, then drop by many, by 2 maybe, or by 3, or by, that doesn't matter. And then increase by 1, 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 then drop by 5, then increase by 1, increase by 1, then drop by 1, then drop by 1, increase by 1, then drop by many, like this. Okay? And so the number of steps then here will be not more. So the number of jumps here is actually the number of down steps. So down steps is jumps in the number of iterations over the while loops. So this is number of while loop iterations. Okay. So on the one hand, it is just the drops of the while of the prefix function, but this is on the other hand, we can see that from the code that this is the number of, this is where the prefix function like loses its magnitude. Okay. So the number of drops is the number of loop iterations, but we see that each step prefix function increases by 1. So we have not more than, we have n steps, and it is at most 1, right? So it can have more than linear number of jumps down, linear number of falls. So you see first. Okay, maybe we should come back to the. Oh no, we are here actually. So why I drawing here then? The question is why. Okay, so here. So once again, first observation is that number of raises, so steps above forward, steps towards the increasing of the prefix function. Number of phrases, подъемов, да, not more than n. Okay, because each step. So this is the 1 position. This is 2, and so on. This is This is position I. This is position n. -1. Okay. So because each step we can increase the value of prefix function by 1, only by 1, not more. So in total we can have at most n jumps and n raises, right? That's clear. Second, number of false is not more than number of raises. So because prefix function can be less than 0, we cannot fall more than we rise. Okay, so number of falls is not more than number of raises. So it means that it's not more than n. So number of falls is bounded by n. And third, number of falls is equal to number of while loop jumps. Iterations. So you see this while loop inside of the prefix function, or in other words, these jumps. Oh, sorry, these jumps. These jumps. So these jumps. So number of falls is actually it is exactly this. Events. So whenever we fall, so whenever the prefix function fall, it means that we jump in the we made the while loop iteration. Okay. Yeah. So that means that number of falls, so number of loop iterations is not more than n. So this while loop in total will do not that much job. We'll do n operations in total, like at most linear time operations. So that means, следовательно, time complexity is equals to big O of n. This is the graph of prefix function. Okay, any questions, guys? Does it make sense? Okay, raise your hands if it is clear for you. Like everything? Where are the others? Okay. Are you guys with me вообще? Are you guys with me вообще, Дим? Так, okay. That is the prefix function algorithm. So the proof is quite beautiful. Quite beautiful. So and the algorithm is itself, it's beautiful, and so it have many applications. Not only not only this one, not only this problem, but many other problems as well. For example, So I will leave it as an exercise. You can solve such kind of problems like exercises. Given S length of S not more than, okay, just given S, and find number of different substrings. Substrings in big O of n squared time. So n is the length of the string. Okay, this is an exercise. Okay, let us do a pause for a few minutes, like a little break. Okay, let's continue. So now we're gonna discuss a bit. We start a new chapter, which is called graphs. So that is graphs representation. So did you start already? Oh, you had the discrete math course, right?
Yes.
All right. So you remember what is graph. So what is graph? So you must remember. I mean,
It is dependence of two variables.
no, graphs. I mean, like it's not like graph, не график, а graph. Не график, а граф. Как Монте-Кристо, как. Не график функции. So what is graph? So you had this on your discrete math course. So let me show you. So like we have a social graph. We have a graph of the roads in like on the map. And we have graph of the friendship graph. We can have genealogical tree, which is also a graph. So what is the graph then?
It's like a figure that have vertices and edges.
Yes, it's the vertices and edges. So graph is like a set of vertices, a set of edges. And what is edge then? So vertices is just like say numbers, like vertex 1, vertex n. And what is edges? What is edge? So edge is a pair that connects at vertices. So like V1, U1, V1, U2, U2, V2, and so on. So like we can have M edges. So the example is going to be like this. Like this, okay? Maybe like this. Okay, this is the example of the graph. This is the example of the graph. So n equals, we have one, so let us number the vertices. We have 6 vertices, n equals 6. And we have edges. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 6, 3, 4, 3, 6. Oh, and it's 1, 5 actually also. Yeah, 3, 4, 5, 6, and 4, 5. And 5, 6. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 edges. 11 edges. M equals 11 edges. M is usually stays for number of edges. N stays for number of vertices. M 11 edges. Okay, so the way we can represent the graph, you actually already had this on the discrete math, but we will see that. Let me remind you, and we will see how to do that on the practice, like how to store the graph, how to represent the graph, and so on. So these are number of the edges, and we can do that. We can represent the graph in various ways. So remember, you had types of graphs. We have two general types. So you see, edges here are undirected. So it means that there is no direction of the edge. So this is edge without an arrow, edge without a direction, which is not necessarily the case because, for example, roads in the Almaty, as you know, or roads in any other city can be one directional. So you can think of vertices as the junctions and edges as the roads between the junctions. Junctions at the pericrostic. So the roads can be one directional, apparently. Or you can think of this as a cities and the flights between the cities, or roads between the cities. Doesn't matter, actually. So the types of graphs, we can have a directional graph or oriented graph. Oriented, so it means that edges are oriented, and or directed. There is direction of the edge. And undirected, unoriented, usually don't say unoriented, just undirected. What? Those are the types of the graphs. And we will store different, so we will store it in the same fashion, actually. So we will not distinguish these cases, but you should know there is a distinction between these cases. So the first option, so the main question is how to store the graph. How to store the graph. So how to store it in the code. That's what it means. Okay. So the first option is adjacency matrix. Adjacency matrix. So what it means, it's n matrix. It is n matrix Aij and what it means. So let me draw it and then explain. So like n9 matrix. So n9 matrix, where ijth entry means that if so A of ij equals 1 if there is an edge ij. So there is an edge, from I to j, and 0 otherwise. Okay, so ijth entry equals to this, and that's it. So for example, we can copy this graph. And try to draw the adjacency matrix. Actually, we can draw it like just right here. To have 6 by 6 matrix, we must have 6 by 6 matrix. So let's say 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So from 1 we have edges to, so the main diagonal would be full of zeros if there's no self edges. So loops. The loops is the edges that points to itself. So like the HII is a loop. So there is no loops in this graph. Okay, so 1 goes to 2, 1 goes to 3, 1 goes to 4, 1 goes to 5. It doesn't go to 6. 2 goes to 1, 3, 4, 6, 3, 4, 6. 3 goes to 4, 6. 4 goes to 5, and doesn't go to 6, and 5 goes to 6. And the other part, like the lower triangular part, can be just reflected in case of undirected graph. So in undirected graph, this adjacency matrix will look like symmetric. So this, I mean, it would be symmetric. It will be symmetric. So 1 0, 1 1 0 1, 1 0 1, 1 0 1. So in case of undirected graph, it is always symmetric matrix, because if you can go from I to J, it means you can go from J to I. So AIJ equals AGI. So that means that in undirected graphs, adjacency matrix means матрица смежности. Adjacency matrix is symmetric. So adjacency matrix is an important matrix, for example, in combinatorics, in mathematics. And so this is like very suitable way of knowing, of storing the graph. Like not that compact. It requires big O of n square memory. So adjacency matrix so prospectives, so it means positive, pros and cons, and consequences, some negatives. So prospectives are like big O of one edge detection. So I can detect an edge between two vertices in linear, in big O of one time, just checking if A of ij is equals to 1. This is the only perspective of adjacency matrix, actually. And consequences, like memory. So first is the memory is big O of n square, which is a lot. So we need to compare, like we need to, like n square is a lot. So if number of vertices is quite there are lots of vertices in the graph, then you cannot store adjacency matrix. For example, the social graph, like for example, you say the Instagram or Facebook, some social network, it can, like the vertices are the people and the edges is the relation between the people. It means that friendship or following. So I follow you, it means that there is an edge from me to you. Okay. And in this graph, there are lots of people, but not that many connections. So the adjacency matrix will be very sparse. So it could contain a lot of zeros, right? So not everybody follows everybody. Actually, in reality, like I follow like 1,000 people, and that's the limits for most of the people. So a lot of people would have not more than 100 edges, but number of people, 1,000 edges, and number of people is milliards, right? Or million, like number of users. So this is not effective. This is requires a lot of memory. So in case of adjacency matrix is sparse, it is not effective. Also, iterate over neighbors is big O of n. So in order to obtain all the neighbors, I should iterate over entire row. and determine if it's 1, then it's a neighbor of the vertex. If it's not 1 at the corresponding column, then it is not a neighbor. So it's linear time. Okay. So another way of storing is the second option. If so-called adjacency lists. Okay. So for example, instead of storing entire matrix for that graph, so let us put that graph a bit slower. Okay, so in case, so in other way around, we can store not all the pairs, like, so we actually store all the pairs, like all the pairs ij, I from 1 to n, j from 1 to n. Instead of that, we can just for a single vertex, store for a single vertex vertex v, or for each single vertex. Okay, for each single vertex v, we store vector of neighbors. GV. For example, G of 1 is equal to 2, 3, 4, 5. 2, 3, 4, 5. G of 2 is equal to 1, 3, 4, 6. G of 4 or G of 3 is equal to what? What G of 3 is equal to?
1, 2, 4, 6.
1, 2, 4, 6, correct? And G of 4?
1, 2, 3, 5.
1, 2, 3, 5. And G of 5 and G of 6. So remains to define G of 5 and G of 6. G of 5 is 1, 4, 6. And G of 6 is 2, 3, 5. So this is the adjacency lists. So for each vertex, we will store the the neighbors of that vertex, and that is enough to for everything in the graph. So we can restore any information from this information, right? But time-wise, and so not time-wise, but I want to say that memory-wise, memory taken for storing the adjacency list, okay, memory, just without excess words, memory in that case is going to be big O of m, where m is number of edges. Why is this so? So this is not the trivial one. This is not the trivial one, but interesting quite. I'm sorry. So how many? So what is the why the memory? So the number of vertices or the number of elements, sum of number of elements in all the lists, adjacency lists, is comparable to M. So it means that actually in reality, some of the sizes of GIs, I from 1 to n, sum of the sizes is equals to exactly to M. Why it is so?
Because it's undirected graph, so we will save each edge for each vertex. Then it should be 2M.
Each edge for each vertex, and why 2M? Why not 10M?
Because we will save, for example, it's undirected graph, so each vertex it should be save each other. For example,
so you mean like each edge is
yes, each, yes, I mean there should be
на русском скажи, что ты по этот?
Да, типа чат 1, это сохраняется на, например, 1, 3, да? То есть они друг другу сохраняют вершины, типа есть связь между ними, либо.
Блин, нужно конкретно сказать, ребят. Не надо, надо сформулировать мысль, а потом говорить. 1, 3, вот это один связанный, так вот получается. У тебя вот так. Я понимаю, что ты понимаешь, Ханат. Я знаю, что ты понял, почему. Но надо объяснить теперь. На работе вас спросят, почему там вот так вот, а вы такие, все. И все, вас уволят. Давай, Ханат, почему еще раз? Ханат это был, да? Ханат?
Да.
Ну, почему 2М? Все, обиделся? Ханат?
Да. Ну, я сказал уже.
Нет, можешь нормально повторить, без запинаний, без сформулированным предложением? Какие обидчивые стали вы, ребята. Ужас. То молчат, то обижаются. В общем, каждое ребро, в каждое ребро встречается ровно 2 раза в этих списках. То есть, например, возьмем ребро 1, 3, оно встречается в списке вершины 1 и встречается в списке вершины 3. То есть в списке 1 вот вершина 3 вот здесь вот, в списке 3 вершина 1. То есть утверждение каждое ребро встречается ровно 2 раза в этих списках. То есть оно представляется в этих списках ровно 2 раза. А значит, в сумме это будет 2m. Это называется лемма рукопожатия. Handshake lemma in mathematics. Handshake lemma. And this lemma is useful for estimating the memory of the adjacency lists. Okay. Okay, so we have the time is over for today. We'll continue in the next week. Okay, goodbye everybody. Thank you for your attention.